To summarize our discussion of partial and semi-partial correlation coefficients, the partial correlation coefficient is the correlation of an explanatory variable with the response variable while holding other explanatory variables constant. And the semi-partial or part correlation is a measure of unique contribution of an explanatory variable to explaining variation in the response variable. We've used this diagram here, and all the different parts of the diagram are indicated with these letters. And we have the notation that we can use to indicate a semi-partial, showing that we are removing some of the variation of a variable from the explanatory variable, whereas in the partial correlation, we're removing a variable from both the explanatory and response variables. Some consideration when dealing with covariates in multiple regression. Theoretical considerations are important. It is not a matter when you create a regression model that you should simply be looking for what can I do to predict a response variable with the quantitative explanatory variables that I have in hand? How can I explain most of the variation in the quantitative variable and build a model in order to get the best fit you possibly can? Because the problem with that is when you switch data, you're going to get different results. You should always be in science trying to develop theoretical understanding of causal relationships, and then use the data to help test your understanding. So always consider, is this theoretically an important variable? Individual variable contribution will vary across models. That means that just because you see a variable, an explanatory variable, that is not actually explaining much of the response variation in one model with certain variables, you shouldn't assume that's going to be the case if you switch to other variables. So it's always the idea of the presence of an explanatory variable in the presence of other explanatory variables. And as soon as you start changing some variations or some variations of variables, what you might find is that one explanatory variable does well in one model, not so well in another model, maybe in between in a third model, even though it's the same explanatory variable. Multicollinearity among explanatory variables leads to difficult interpretations of individual variable value. So beware and watch out for multicollinearity, and that is, there are really two reasons why I always start by looking at zero-order correlations. One is to see if I'm considering a variable that's not related to anything, not related to my response or to my explanatory variables. Now, if it's not related to the response variable, but it is related to some of the explanatory variables, you might find that a variable that's not related to the response is related to the response when you pull out the effects of the other variables. That is, even though the zero-order correlation might be near zero, it might be something substantial in terms of looking at semi-partial or part correlations. So that can happen. But the other reason that I look at zero-order correlations is to make sure that none of my explanatory variables are correlated too high with each other. What do I mean by too high? Strong relationships, 0.8, 0.85, 0.89, 0.91. Those are strong relationships. And in that case, I probably should be only choosing one of them to serve as the proxy for both of them, because they are so similar in terms of what they are explaining that I could have funny things happen if I put them both in the model. And I'm going to demonstrate that right now. I'm going to use some blood pressure data. So let me go ahead and load in my blood pressure data. Multicollinearity refers to a strong relationship among two explanatory variables, and when this occurs, you can obtain misleading results when both variables are included in the model. Given the strong relationship, one of the variables can in essence serve as a proxy for both. So the data here is from individuals with high blood pressure, and we're going to build a model that looks at blood pressure as a function of weight and body surface area. These are two variables that likely will influence blood pressure. So let's go ahead and look and see what we get. This tells us that if we hold the body surface area constant, that weight increases blood pressure, and notice the slope here, notice the estimate, 1 millimeter of mercury for every 1 kilogram increase. If I were to show you the actual code book for these variables, which I could actually do that right now, we see that blood pressure is given in millimeters of mercury, age is in years, weights in kilograms, body surface area in square meters, duration of hypertension in years, pulse in beats per minute, and then a stress index with higher numbers indicating higher stress. So going back to the notebook here, we see if we remove the effects of body surface area, that with weight, we get an increase of 1 millimeter of mercury for every kilogram that we increase the weight. We also see here that we get 5.8 millimeters of mercury increase if we hold weight constant. We get 5.8 millimeters of mercury, but we're also given a little flag here, a little signal from that relatively high p-value that this may change. If we look at other data sets, this is not very stable because of the large standard error here of 6 relative to the estimate of 5.8. Well, not surprisingly, look what happens if we look at the correlation of weight and body surface area. Not surprisingly, they are highly correlated, 0.88. So let's look at two individual models, one with just weight and one with just body surface area. With just weight, we get an estimate of 1.2. That's not much different than what we had with the full model. With the model with both in there, we had a 1.03, and now we're getting weight being 1.2. We estimate an increase of 1.2 millimeters of mercury for every additional kilogram. What about if we do body surface area? Oh, whoa, that changed things substantially. Remember up here, it was 5.8 when we put it in with weight. But notice when we have it all by itself, that it's 34.4. We went from estimating an increase of 5.8 millimeters of mercury per square meter to an increase of 34.4 millimeters of mercury per square meter. The high relationship of weight with BSA was squelching the estimate of BSA on blood pressure. We put in weight, then we put in BSA, and weight had already accounted for much of the same thing that BSA would, and so it was squelching this. The influence of multicollinearity, however, can extend even beyond the two variables that are correlated with each other. Let's take a look at this model. This model has in weight, it has BSA, it has duration, it has pulse, and it has stress, all of our explanatory variables. And when we put all those explanatory variables, we see that, again, BSA is not very stable, nor are any of the other variables. The only thing really that is helping us out here is weight. It's got a small p-value of 0.005. We have an estimate of 0.8. Remember, the estimate when it was by itself in the model was about 1.2. Let's remove weight from the model and see what happens. When we remove weight from the model, all of a sudden, not only is BSA important and stable and goes up to 26, but also pulse becomes stable. and Pulse has a 0.62 of mercury for every beat per minute. So BSA is stable, Pulse is stable. The Pulse slope estimate's about 3 times higher than we saw up here in this model where it was 0.21. Now it's at about 0.62. So the bottom line is that when we have highly correlated explanatory variables, we should not include them in the model together. So let's build a model. Before we begin, we should think about what are our theoretical expectations. Which zero-order correlations suggest strong covariates, but more importantly, which ones maybe suggest that we have 2 variables that are highly correlated so that one explanatory variable could basically serve as having both in without the problems of multicollinearity. So one variable serves as a proxy for 2, and on the other side of the spectrum, are there any explanatory variables that aren't related to anything, the response or other explanatory variables? Do any of the correlations prompt us to investigate multicollinearity? Is there any evidence of confounding or suppression when we start looking at our potential models? We need to think about what we've learned in past videos about confounding and suppression and see if there's any evidence of that. What do the regression coefficients, the partial correlations, and the semi-partial correlations tell us about our model? And can we achieve parsimony? Can we have a good model that's easy to explain, that makes theoretical sense, and easy to explain often comes hand in hand with not very many explanatory variables? Obviously, if I lose a lot when I remove a variable, I'm going to think carefully about, do I want to remove that explanatory variable? But if I can remove an explanatory variable and still have a good model, and one maybe that makes more theoretical sense to me, then I should consider that.